worked out this algebra of conformal transformations. Okay, we did the conformal transformation z goes to z plus f of z. Okay, followed by another conformal transformation z goes to z plus g of z, and we worked out an algebra of conformal transformations. Okay, I'm going to do a couple of manipulations in this class which are related to this algebra, and you'll see the relationship. And you remember that the generators of these transformations, the currents that generated them were Jz was equal, Jf was equal to T times F. Okay? Okay. I'm going to say basically the same thing, but in a language that is sometimes useful, which goes this way. Look, suppose I'm doing a path integral, and I've got an insertion at the origin, but no other insertion inside a disk of some radius. You can call it the unit disk if you want. So there's some radius where I've got no other insertion, where I've got no other insertion. Okay, I'm going to study the z operator, the T of z operator, insertions of the T of z operator inside this unit disk. What do I mean by that? What I mean by that is I'm looking at a path integral with insertions, arbitrary insertions outside the unit disk, T of z here, and perhaps an insertion at the origin. That's what I'm looking at. Okay? And I'm going to look at all of these correlation functions. When I make statements about, let's say that this function, this is analytic in z, what it means is all of these correlation functions are analytic in z. Okay, so when I talk about the z dependence of something, I mean the z dependence of all correlators of this one. Okay, so the first statement, the one that you all know very well, is that all these correlators are analytic. So del z bar of tz is equal to 0. How did we know that? That came from the Ward identity. You see, the Ward identity told us that T was a conserved current. Okay? In fact, all of these were conserved currents. Okay? It had only an analytic component and no non-analytic component. So conservation of that current from the Ward identity was simply the statement that del z bar of this was 0. Now, what was the Ward identity? The Ward identity is a statement that correlation functions of T obey this equation provided T doesn't hit any other insertion. So I've been very careful. I've made sure there are no other insertions inside this unit disk. Okay? So in this unit disk and away from the origin, this T of z is an analytic function. Is this clear? Now, any such functions, we're going to allow for operators inserted at the origin. So we will not demand that T is analytic at the origin. It need not be, because of the contact terms of the Ward identity. Okay? So any function that is analytic like this can be, everywhere except the origin, can be expanded in a Laurent series. Okay? So I'm going to make the following expansion. T of z is equal to sum over m. M is equal to minus infinity to infinity, Lm divided by z to the power n plus 2. You can ask why 2? Well, we'll see. But basically the 2 is a reflection of the fact that T has holomorphic dimension 2. That's why it's a matter of convention, of course. But the convention, this is a useful convention because T has dimension 2. Okay? And go on. T is a local operator, yes.
And these insertions are
also operators. Okay? So all we are...
these are at particular points.
These are at particular locations. Let's say x1, x2, x3, x4. Right?
At every
No, Tz is also at a particular point.
okay, that's it.
Then I vary this particular point.
That is
And I ask how the correlation function changes as I vary that particular point. So this correlation function is a function of many variables. one of the variables is z. When I say this statement, what I mean is I hold all other variables fixed and vary only z. Is this clear? So it's a clear statement about correlation function. And we sometimes, I sometimes loosely say this statement. What I mean is that it's true for any correlation function. And there's always statements about correlation functions. Okay? Great. Now, I take this object here, and this object for me defines an operator, not a local operator, an operator Lm. How do I, if I wanted to get this operator Lm, this is now an operator acting in Hilbert space language on radial slices. How will I get it? Well, I just invert this formula. Lm is equal to integral z to the pi m plus 1 t of z by 1 by 2 pi I. Using Cauchy's theorem. Okay? Now, I'm going to ask the following question. These operators, LMs. First question I'm going to ask is, what is the algebra? What do I get when I compute an LM with an LM? Yes? Yes? I didn't understand.
Writing OP of TP, then I'll have terms with a singular.
You see, see, this is true in every correlation function for arbitrary insertions here. What you are pointing out is that that insertion was a T. Then on that, for those correlation functions, all LMs for m less than a certain maximum would be 0. That would be the statement that various LMs annihilate the state dual to the operator T. However, there may be other states in the world. Not all states are created by acting with T at the origin. There could be some other operator here which would trigger one of those higher LMs that annihilated the state created by T. Okay? So I'm writing this in general, keeping the keeping completely agnostic about what operator it is. Is this clear? Okay? It's a good question, and we will do exercises like this. Okay, we'll come back to that way of thinking as we move on. LMs have the dimension they have by this counting. We didn't want to look at local operators. You see, given a local operator, I can always take x to some power and multiply it and integrate it. So no matter what the dimension of the local operator was, by choosing the power of x appropriately, I can get all kinds of dimensions for this integrated operator. This is not local. It's one of these things, right? Smearing with x's. Okay? The constraint is on dimensions of local operators. Okay? This is an operator in the sense of operator on Hilbert space in radial quantization. Is this clear? So you should think of this as an operator in this language. Okay? This dz, where we think of the contour as being a radial contour, I can think of it as a circle, but I don't have to because of analyticity. I can deform it as I want. Okay? And then but if I thought of it as a circle, it's clearly acting on Hilbert space of states. Is this clear? Okay. So let's keep going. So the question I'm going to ask is, what is the commutation relation between LM and LN? Well, see, this is basically the same as this question, but I'm going to say it in this language because it's useful. Okay. So what is the commutation relation between LM and LN? So this is the kind of manipulation we've done before. I'm going to do it 3 or 4 times in today's class just so that you get used to it. Okay, it's a kind of manipulation that you guys will soon be doing in your sleep. It's very simple manipulation. Okay, the constraint is on dimensions of operator on Hilbert space of states. Is this clear? Okay. So Okay, so this is the manipulation with two colors, if we have two colors. Okay, so let's say LM, suppose I want to compute LM and LN. LM is the guy with the blue contour, and LN is the guy with the green contour. So LM, LN, so this, the first term in this commutation relation is this, because things earlier come to the right, and inside is earlier. Do you understand? So this minus this is the commutation relationship of LM and N. Is this clear? Now, as we've done before, it's really the same calculation as you see. One we did last class, just doing in a different language. As we've done before.
There's no singularity within this research.
What?
There's no singularity within.
There could be.
No, I mean between in the annulus.
In the annulus, there's no singularity, because we've assumed that we're doing this calculation in the disk. Okay? So now, as we've done before, we'll imagine that these two green circles are the same, but the blue one has gone just above and just below. Then we do the blue contour integral. So the green circle, on the green integral, we've got a particular point. So the blue contour integral becomes this one. Everyone's comfortable with this manipulation now? It becomes this one, and then you have to integrate over the point around which you did the integral. Okay? So what we need, but this just gives you a residue. So let's see. So now we had 1 by 2 pi I, and then we had another 1 by 2 pi I. Then we had a z to the power m plus 1, w to the power n plus 1. Okay? Z to the power n plus 1, w to the power n plus 1, and t of z, t of w. And we're supposed to do the z integral around the w contour. Okay? So that's 1 by 2 pi I times 1 by 2 pi I, and then we use the operator product algebra that we developed last class. Okay? So we use w to the power n plus 1, c by 2 by z minus w to the 4, plus 2t of w by z minus w the whole 6 squared, plus del t of w by z minus w, and z to the power m plus 1. Okay? Now, in doing the z contour, we just want to fill out the poles. So we could get poles from here, here, or here. How would we get a pole from here? From here? Well, if we take the z thing and Taylor expand it. So let's write this. So w is w, but let's write z as z minus, Taylor expand this, so around the point w, exactly. So we'll write z is equal to w plus m plus 1 z minus w plus m plus 1 into m by 2 z minus w squared plus m plus 1 into m minus 1 by 6 z minus w cubed. We'll never need higher than this.
So that's z to the m plus 1, right? This is not just z. That's the expansion of z to the m plus 1.
Yeah, absolutely right. You're absolutely right. So this is z to the power m plus 1, and I should be putting various. This is m plus 1.
Yeah.
This is w to the power m, w to the power m minus 1, w to the power m minus 2. I've taken various derivatives. All clear? Okay. Now we insert this Taylor expansion into this expression here. And you see that various terms here click with various terms here to give you poles. The residues of those poles give you the Cauchy integral. So what do we get from the first term? Well, we get c by 12. Firstly, when we take the Cauchy integral, one of the 2 pi I factors cancels. So we have 1 by 2 pi I times c by 12. 12 is because it's 6.5. m into m into m squared minus 1. Okay? And now what's the power of w? We have w to the power m plus n minus 1. Okay? That's great. We got this term when we clicked this with this. What about when we click this? What about when we click, this with this? Okay? Then we get plus m plus 1 into w to the power m plus n plus 1. And that's it. I'm going to multiply the whole thing by t of w in a minute. Okay? Oh, sorry. Here, this one has a t of w because the OP had a 2t of, and then there's a factor of 2 because I'm using this OP. Okay? Yeah, that looks good. And then there is the last one where we use no Taylor expansion at all and hit this guy. Is this clear?
Should there be a factor of 2 because this 2 will, oh yeah, it will be, right.
Right, because it came from here.
It will be there.
Okay? And then there is the last term which used no Taylor expansion at all, but came from this guy. So there was a plus del t of w, and w to the power m plus n plus 2. All of these things have to be integrated dw. So that's the answer for this commutation relationship. Okay. Now, let's process this. First term, what do we get?
Delta m minus n.
C by 12 delta of m plus n comma 0, as you said.
Yeah.
Okay? What about the second term? Now, the second term and the third term are going to come together. In order to understand that, we're doing an integral over closed loop, so we can integrate by parts on the third term. So when I do that, I pick up a minus sign, and then the minus sign has the derivative hitting this guy. The derivative hitting this guy produces an m plus n plus 2. Okay? So I'm going to write both terms together, but you check me and you see if I'm not making a mistake. I hope I've got my signs right. It's a bit odd. Anyway, let me see. I do that, and what do I get? I get minus m minus n minus 2 plus 2m plus 2. And then the integrand is the same. It's always w to the power m plus n minus 1. So I can that's why I can combine this term and this term together.
Yeah.
Okay? But that, by this definition, was just L of m plus n. Okay. Okay, so let's write this better. This as always, thank you. Thank you. So we get L of m comma L of n is equal to m into m square minus 1 c by 12, okay, plus m minus n L of n plus n. Anything else? What? No, it gets a delta. delta of m plus n comma 0. Thank you. Okay. What is this statement? You see, what we've said here is that T, T we knew was a conserved current. But we knew more than that. It was an analytic function. Okay? So T weighted by any analytic function was also a conserved current. We chose these weighting factors to be Z of m, these Z of m plus 1s to define a new current. And we found the charges corresponding to these new currents. That's what these LMs are. This makes contact, by the way, with what we did last time. You remember the charges corresponding to a conformal transformation with f of x was f of z, t of z. These LMs are simply those charges with the particular choices f of z is equal to z to the power m plus 1. Okay? And this algebra is the same as the algebra we computed last time. We computed the algebra last time in terms of LF and LG. If you plug f is equal to z to the power m plus 1 and g is equal to z to the power n plus 1, you'll recover this algebra. Okay, I just want to do it once again in language that you might see. That's sometimes useful. Okay? This algebra is called the Virasoro algebra. And reflects the fact that our theory has an infinite number of conserved charges. Or infinite number of, because there are infinite number of analytic currents. T of z multiplied by any function of z. We chose the basis of these currents. Okay? And the algebra of charges is an interesting algebra. Okay? You take L of m and L of n. Had it not been for this piece, it would have been like a harmonic oscillator algebra. The creation annihilation operators. Okay? But there's also this piece. Okay? So that piece is what you would get, as Indranil pointed out last class, from classical diffeomorphisms. The operator z to the power m plus 1 del z, if you allow this as the representation of that operator ln, and you compute the commutation relations, that would give you this. This is the additional piece coming from the fact that conformal transformation is not just diffeomorphism. There's also an element of wild transformations. So that C part is the wild transformation part in the conformal transformation. And we will see either in this class or the next how to make that explicit. How to use C to understand how things transform under wild transformations. Had it been that the conformal field theory did not transform under wild transformations, then C would have been 0, because then a conformal transformation would have been a pure diffeomorphism. The fact that it's not a pure diffeomorphism is this term. So this term contains all the information of how the theory transforms under wild transformations. And we'll make that explicit either in this class or the next.
This includes the prefactor of m squared, right? So is there a reason that the plus minus 1 and 0 sort of don't see the wild part?
Yeah. Okay, excellent. So the fact that the plus minus 1 and 0 just don't appear. Okay, so let's now focus.
There's a delimitation, right?
Exactly. Let's focus on the plus minus 1 and 0 and look what it gives you. The first thing to notice is that if we just do plus minus 1 and 0, I wanted just a minute. Which ones did I want? Just one second. I wanted z, and z squared. And this is plus minus 1 and 0. Yeah, perfect. Perfect. Yeah, and it's this thing. Thank you. I was wondering why. Yeah, sorry. Yeah, the first thing to understand is that L plus minus 1 and 0 form a closed subalgebra among themselves. Okay, so let's try to understand that. Well, it's obvious, right? Firstly, as you pointed out, this term is not there. It would have been closed anyway, but anyway, this term's not there. And the second thing to note is that if you do, let's say, L1 with L1, which looks like the potential of taking you out of this, you get 0 from here. Similarly, with L minus 1 with L minus 1 gives you 0. Okay? L1 with L minus 1 will give you an L0, and so on. You see that it's closed. By the way, if we had chosen minus 2 to 2, that would not have been closed. Why not? Because we did L1 with L2. That would give us L3 without this coefficient being 0. And then we did L1 with L3, that would give us L4, and so on. Okay? So this plus minus 1 and 0 was very specially chosen so that you got a closed subalgebra. Okay, firstly you got this closure. Secondly was the point that you made. Not only do we have a closed subalgebra, we have a closed subalgebra without an identity piece. What this means is that these symmetries form, they're represented like a Lie algebra. It's like FABC without an identity piece. Okay? This is a reflection of the fact that these symmetries are preserved by the vacuum. There's another way of saying it. Let me say it firstly in this other way. Okay, I'm going to say it. I hope it makes sense. But as we go on, it'll make more sense. Okay, I want to explain to you, you see, what we're doing here is transforming by a vector field. All our analysis was local. But you could ask, suppose we were on the sphere. Suppose our field theory was an S2. Right, exactly. Suppose we were looking at an S2. Okay? You can ask, are these vector fields well defined everywhere on the S2 or not? Okay? Now, there are two places where they might go bad. They might go bad at z equals 0, or they might go bad at z equals infinity. Okay? Let's first look at z equals 0. Z equals 0 is very easy to see. Okay? Because this is a vector field. If m plus 1 is greater than or equal to 0, that is, m is greater than or equal to minus 1, this vector field is well behaved at 0. If m was less, didn't obey this inequality, this vector field would be problematic at 0. Is this clear? Now what about infinity? Okay? Now what about infinity? The way to think about infinity is to do a conformal transformation. See, the conformal transformation is just, okay, let me just say it and then we'll discuss it. The way to think of infinity is to do a conformal transformation, which is make the change of variables z is equal to 1 by w. If I make this change of variables, then I bring infinity to 0. So in this new variable, the vector field should be well behaved at 0. Okay? So let's check. So what we get now is 1 by w to the power m plus 1. Okay. Well, up to psi. You see, z del by del z will go to w del by del w. Okay? So we've got z to the power m, which will go to w to the power minus m. And then we'll get w del by del w. So we get w to the power minus m plus 1 del by del w. We'll do the algebra first and then I'll tell you what physics is. Okay? Now this has to be well behaved at 0, which means minus m plus 1 has to be greater than or equal to 0, which means m has to be less than or equal to 1. Okay? So m has to be greater than or equal to minus 1, m has to be less than or equal to 1. So the vector fields that are well behaved both at 0 and infinity are m equals minus 1, 0 and 1. Okay. Go on.
Special conformal transformation and
parts, now there is this shift in the limit we add. In your special conformal transformation,
Yes. You're saying apart from the continuous things. Yes.
the one that you are doing here is, you are doing that quantity, right? You are not really doing the one that is in the conformal group. This is the one that is in the conformal group, just going to 1 by W. All I am asking is that is there this...
It's an analytic change of variables.
It's an analytic change of variables and it's in the right group.
Yes.
It's in the right group.
Yes.
In higher dimensions there is this, some theories which deserve parity as well,
Mhm.
and then you can do little bit more. You can do little bit more in the sense that you can probably do Z going to 1 by Z bar as a part of your symmetry.
Let's see. So if you want to mix Z and Z bar, that sounds just like, it's like Z goes to 1 by Z, and then Z and Z bar interchanged.
Yes.
This flip. This flip is like changing what you mean by left movers. So exactly, it's a parity transformation. So if your theory is invariant under parity, Z goes to Z bar is just that parity transform. Yeah, we're not good. Yeah, we could do that in any theory that's invariant under parity. We'll sometimes mod out the theory by this symmetry. Yes. Go on.
In 3-point function of space tensors,
Yes.
I heard like a theory that there are these equivalent structures in, let's say, in 3 dimensions,
Yes.
4 dimensions, and so on.
Yes.
Here it will be completely, it will be the same for polynomial and working theory.
It's totally
So
different.
there is no extra structure.
All correlation functions of the stress tensor
are determined.
are determined by a Virasoro algebra.
Determined by Virasoro.
Completely.
So, if you repeat those arguments in 3 dimensions, which gives you this quantization of space tensor, which is this inequivalent structure, why would it just...
You see, all of the interesting inequivalent structures came from index structure.
Yes.
Okay? But here there's no interesting index structure because there's no talking between T and T bar.
Because of holomorphic,
Because there were 3 possible index structures, right? There was TZ, Z, TZ, Z bar, and TZ bar, Z bar. Then tracelessness of the stress tensor forced TZ, Z bar to be 0. And then because of holomorphicity, the TZZ and TZ bar, Z bar just completely decoupled. So then this T behaves just like a scalar. So in fact, as you will see, as we will do this today, in higher dimensions, it's well known that scalar operators have a unique 3-point function.
yes. So this is that statement now.
Yeah, so all operators here behave like scalars because they behave like scalars under the holomorphic part of the conformal algebra. So 3-point functions of all holomorphic operators.
You
Just
can-
totally determined.
You can take T for complex, one holomorphic or anti-holomorphic.
Exactly. And then, as far as the holomorphic part is concerned, it just behaves like a scalar under this holomorphic part. So it behaves just like a scalar in higher dimensions. Okay, we will see some. We'll see some of this. Okay, so excellent. So now I'm going to give you 2 minutes about what. You might wonder, okay, so what if there are some vector fields that are well defined all over the sphere? Why should I care? Why you should care is basically, see, for various things. You see, suppose I had this cylinder theory. Suppose I had this theory on the cylinder. Okay? And I wanted to do some symmetry transformations on states. Okay? The fact that this field is well behaved both at 0 and infinity. Okay? We basically will transform to the statement that the vacuum of the theory, in fact we will see this very soon, is annihilated by all these 3 operators. L0, L minus 1, and L1. Okay? So now, suppose you were not as sophisticated as we've become now. You were just doing Schiff level quantum mechanics. You wanted to check if some correlation functions preserve a certain symmetry. Okay? The kind of arguments that people do are the following. Suppose I have a generator of that symmetry. I'll call that generator G. Okay? I've got a vacuum, then I've got some operators, O, x1, O, xn. And there's the vacuum. I want to check whether transformed O's have the same correlation functions, okay, as the correlators without the transformation. I'm going to check this infinitesimally. So what I do is I act with G on the right. Use the fact that this is 0 because G annihilates the vacuum. That's like a key point. Okay? Then I take G through to the left. And then I use the fact that it's 0 because G annihilates the vacuum from the other side. Now G annihilating the vacuum from the right is, is going to be tightly related to the fact that the vector field was well defined as 0. And G annihilating the vacuum from the left will be tightly related to the fact that the vector field that G annihilates the vacuum from this side. Okay? So this vector field being well defined, we will see as we go on. But this vector field being well defined is basically closely related to the statement that this G annihilates the vacuum both ways. And that's why it's like a genuine symmetry of the theory. Okay? Now if you've got a genuine symmetry, some genuine symmetry, it obeys like, in correlation functions, it obeys Lie algebra type relations without this extra constant piece. So this is related to that fact. Okay? Okay. I'm sorry it was so rough. We'll see more of this as we go. Other questions, comments? Yes? Where did you, the total number of global conserved charges, absolutely correct. And so this is 3 plus 3. 3 for the left movers and 3 for the right. These were the 3, L minus 1, L0 and L1. But we're focusing just on the holomorphic part. But there's also the anti-holomorphic part. The 3 plus 3 is 6. Right? As you said, it's a SO2 comma 2, which has dimension 6. That's the global part. The conformal part. Global part is just the thing that is well behaved everywhere. These vector fields are everywhere. Okay? Excellent. So let's keep going. Okay. So now the next question we're going to ask is the following. Okay. The next question we're going to ask is the following. We're going to ask the question, suppose I have Lm and I act on a distinguished operator, a distinguished state, namely the state created by the identity operator, which is the state created by a path integral with no insertion. Okay, what do I get? What? We get 0 depending on what? Exactly. So you see what we have is what we've got to do is to compute integral z to the power m plus 1 t of z. Now in general t was analytic everywhere except for the origin. But in the special case of the insertion, at the origin was the insertion by the identity operator, t is analytic also at the origin. Okay? So this thing is a completely analytic function provided m plus 1 is greater than or equal to 0 or m is greater than or equal to minus 1. Okay? So we conclude that L minus 1, L0, L1, L infinity all annihilate the state dual to the identity operator. Okay. In particular, these three objects annihilate the state due to the identity operator. Okay? This state is sometimes called the SL2R invariant state because it's annihilated by these three objects. Is this clear? Now, no non-trivial operator insertion will annihilate L minus 1. Why is that? Because L minus 1 is just d by dz. It's just translations. So suppose you've got a non-trivial operator insertion at the origin and you act by d by dz. What does it do? It moves the non-trivial operator insertion to a neighboring point. As long as the operator insertion was anything other than identity, it was non-trivial, it will be moved. Okay? So the only operator that's annihilated by L minus 1 in this way is the identity. Yeah, because this is the only operator whose insertions in an arbitrary state, or other insertions, are constants. Okay? So this state is very special. The identity operator, of course, is a very special operator. It's not an operator in some way. Okay? And the state corresponding to it is very special. It is the only state in the Hilbert space that is annihilated by the full SL2R algebra, including L minus 1. Okay? So it's called the SL2R invariant state, this identity state. Okay? This connects with this discussion, by the way. So this, when I said vacuum here earlier, what I meant was this identity, the state due to the identity operator, which, as we will prove in any unitary quantum field theory, conformal field theory, is always the vacuum of the conformal. Okay, excellent. Fine. So far so good. Now we want to do a little more. So far we've studied one set of operators in great detail, namely the stress tensor. Okay? Now I'm going to define another class of operators, which are called primary operators under the conformal algebra. Okay? And these primary operators have the following property. So in order to understand what a primary operator is, let us remember the following. Suppose I take the differential operator del by del z, and I ask how it transforms under a diffeomorphism. Okay. So very good. So that's very easy. This is equal to del w by del z, del by del w. Okay. If I took the operator, if I took n copies of this differential operator, it will acting on different fields, let's say. It will transform with n such factors. Okay? Now, remember that a conformal transformation, okay, is a compounding of a diffeomorphism and a Weyl transformation. Okay? So, a key part of the conformal transformation is this diffeomorphism. Okay? So inspired by this, what we're going to do is make a definition. Suppose I have an operator that transforms like phi z, phi in the coordinate z, okay, is equal to del w by del z, phi in the coordinate w. Then I will call this a primary operator. This is just a name, it's just a definition. I will call this operator primary operator of weight 1. More generally, if phi z transforms like this to the power h, I will call this a primary operator of weight h. Okay? Not necessarily. If you build out of del by del z's, it would be. But in general, we will allow h to be a real number. Okay? Now, let us stop for a minute to see exactly what this statement means.
So if it can be even non-integer, then every function is basically primary of some power?
No, because under a conformal transformation, suppose I take an operator that's primary and I look at how its derivative transforms. it will have a term that looks like this, but it will have a term where the derivative acts on this. So it will transform in general differently. Right? So primary operators are quite special. They transform in a sort of special way. Okay? Now I want to explain. I want to understand. Let me explain exactly what I mean by this statement. Okay? Suppose I had some remember what we have is a conformal field theory. So in this conformal field theory, I can do a diffeomorphism plus a Weyl transformation, and I get the same action, let's say, in the new coordinate w as I had in the old coordinate z. Okay? Now, the fact that there are operators that do this, okay, so suppose I have an insertion of one of these operators and any other things. Okay, let's say I have an insertion of phi z at the point z. Okay, maybe it's easiest to say it with two phi z's. So suppose I have phi z at the point z1 and phi z at the point z2. I could dress this with many other operators and many other points, but just for clarity, I'll stick to this is phi in the coordinate z. Okay, we'll soon drop it. Okay, wait. Let's keep it for now. Okay, and I look at the correlation function of this operator. Okay, so I've got phi. I look at the correlation function of this operator. Now, the claim is that the fact that this transforms in this way under conformal transformation is what claim? It is the claim that, see, phi w at the point w1, phi w at the point w2 times and phi z is, so then I need to write del w by del z 1 h1 del w by del z 2, both are h. Okay, where z1 and w1 are related by the change of by the w is equal to w of z. Okay, so for instance, suppose I took this and wrote w as a function of z. Right, so I've got w1, which is w as a function of z1, and w2, which is w as a function of z2. What? They in general are different. This is one function. W is a function of z, but that function evaluates to something at the point z1 and something else at the point z2.
The function is same.
What?
The W functional form is
Functional form is the same. It's just one function. It could be z square. Okay? These two are now the same as functions. This left hand side is now a function of z1 and z2. The right hand side is now a function of z1 and z2. And this assertion of this transformation, okay, what it means that an operator transforms like this is, this is what it means. Is this clear? Okay, right hand side is a function of z1, z2, left hand side is a function of z1, z2, and okay, clear? Okay, so any operator that transforms like this under conformal transformations, and we will see that all conformal field theories have special operators like this representation. And we'll see all this. There always exist such operators, is what I want to say. Okay, is called a primary operator. Now, there are 2 or 3 things I want to do. What? You do it twice, you get the same kind of transformation rule. Yes, that is true, because you just use the chain rule. So as Indranil's point is that if you now do another coordinate transformation, you'd write W as a function of alpha. Okay, what you will get is phi z was equal to del W by del Z phi W to the power h. But phi W is del alpha by del W to the power h phi alpha. And then you use the chain rule and you find that phi z is equal to del alpha by del Z to the power h phi alpha, which is what you would have written in the first place. Okay, so this is true. This transformation rule makes sense. Okay,
So
now.
strictly speaking, this del W by del Z, this will be real, and so wouldn't it be? The factor behind phi W.
Yes.
It has to be real, right? I mean, we have to
Everything
raise by more.
Okay. No. This is an analytic function here.
Oh.
So everything is complex.
No, I mean, if h is in general any fractional value,
Yes.
then I was just wondering whether.
No, it is.
There might be.
You're wondering if there are branch cuts or things like that?
Yeah.
Okay. Are there branch cuts? This is a good question. Yeah. Right. Though, of course, you could have just, there's no mod. Yeah. I mean, it could be that you have an operator that has dimension h and h bar. So then that will transform like you want. This del W by del Z to the power h, del W bar by del Z bar to the power h, and then it's a mod, as Indranil was saying. Okay? But that's not every operator has this form. Now, but you are asking, is it consistent to have an operator which has fractional, it's a primary operator with fractional weight? Maybe when you put all the insertions together. See, certainly, just as a, it's probably true. Yeah. No, you could make h and h bar also different. But what's going to be needed is that h minus h bar will be an integer. This we will see will be a requirement of modular invariance for the real operator insertions in the case. See, there are 2 things I want to say. It's sometimes useful to deal with operators that in intermediate steps of the calculation don't obey this. But in the end, put together different pieces of operators such that the net operator obeys this condition. So for instance, you can deal with an operator that's purely holomorphic times an operator that's purely anti-holomorphic. The purely holomorphic guy needn't obey this, the purely anti-holomorphic guy needn't obey this. But the actual physical insertions you look at in your theory, the things that will be well behaved, well defined and so on, as you said, would need this to be well defined. And this will be sufficient for that.
All you want is a correlation function with single value.
Single valued, exactly.
Why did you use a modular transform?
Okay. Modular transform, see.
It might come out from that, but
It does come out from that. It comes out also from single valuedness. It comes out from that because part of modular transformations is shifts in the circle direction, and that shift in the circle direction couples to h minus L0 minus L0 bar, and that the partition function is invariant under that requires that every state that runs in this has L0 minus L0 bars equal to an integer. The 2 pi. And now, given that the state operator map in a conformal field theory that tells you that all allowed local operators, so things that dual to states, things that run in the trace on the torus, also have h minus h bar is equal to integer. Okay? This will then ensure that their correlation functions are single valued, which you could have anywhere independently. There's a tight connection between the single valuedness and modular invariance. Yes, go on.
Even if you take 4-point function,
Uh-huh.
and then also you can write only as a holomorphic part.
Huh.
I mean that will screw up this thing. So you need to put anti-holomorphic part and sum over
Yeah.
to make single valuedness, and then you will say unless you put the anti-holomorphic part suitably, you will not get modular.
Exactly. Exactly. And as you say, you also will not in general get single valuedness.
Yes. So,
Yes. Yes. What is the motivation for defining a primary operator? You see, one thing is this. Suppose you have an operator that is a scalar under conformal transformations. Then I take a derivative of it. That will make it transform like this with h equals 1. Okay? So suppose in some naive way, you had some operator that was just invariant under conformal transformations. Naively, the operator x in the free boson theory that we started our course studying is of this form. Okay, why is it naively of this form? It's naive, as we will see. But why is it naively of this form? Because what's a conformal transformation? A conformal transformation is a combination of diffeomorphism and a Weyl transformation. Under diffeomorphisms on the world sheet, does x transform? No, it was a scalar. Under Weyl transformations, does it transform? Classically, it doesn't. We started our course by saying that, by demonstrating that the classical action was Weyl invariant when we took x not to transform at all. So naively, x was a scalar in conformal transformation. Right? Okay, so it's very natural to consider scalars under conformal transformations. But now if you have scalars under conformal transformations, that will, by taking derivatives, for instance, you take del x, that gives you a dimension 1 operator by this definition. Now by taking product of many such del x's, we don't want to take del squared x. That may or may not transform nicely, it won't. Okay? But the quantity del x to the power n will automatically transform like an object of weight n. So it's very natural to introduce these objects, at least for integer powers, and then we're just allowing for more general powers. They will turn up. Okay? Yeah. You will only really feel convinced once you see examples, which we will soon see. Is this clear? Great. Now, these primary operators, the first thing I want to understand is how a primary operator, what's the interaction between primary operators and the Virasoro algebra, so the stress tensors. But that's very easy, because I've already told you how a primary operator transforms under conformal transformations. And T's are the generators of conformal transformations. Okay, so I just have to put that information together. In order to help us understand how, what the interaction between the stress tensor and these primary operators is. Okay, so let's do that. Okay. So let's see. So what I tried to explain to you is that this transformation rule means this thing. Now let's take this and implement it for W being Z plus something small. Okay. So suppose W is equal to Z plus f of Z, where f is small, infinitesimal. We work to first order derivative. Got?
This quantity is the SP in this.
Yes.
And I am going to just do a nice integer, it will ensure that is integer. And two-dimensional is strictly because now you one group, you can put anything you want.
Yes.
And then you said that I will just say, I will say that only consider this class of diffeomorphism and the modular transform is a particular kind of diffeomorphism under which I want single valuedness. Your strong statement is that is enough to tell under all the Fibonacci terms they are single value. All holomorphic, this kind of transformation.
Yeah.
So only power is that you are telling me that under this it should be single value.
Yeah. Yeah. And of course, you know, the fact that that this is enough is easy to see intuitively, right? See, suppose we had O1, O2, I look at the OP. O1 with O2 goes to O3. Okay? So now, let's say that this has dimension H1, H1 bar. This has H2, H2 bar. And this has H3, H3 bar. So I'm sorry for everyone else, but I just quickly respond to this question. Okay, so suppose I put this at 0 and I put this at Z. I get O3 at 0. Okay? And what am I going to get? I'm going to get Z minus 0 to the power, I'm going to get Z minus 0 to the power H1 plus H2 minus H3 and Z bar to the power H1 bar plus H2 bar minus H3 bar. Now let's take Z around itself by 2 pi. What's the phase that you get? We get H1 times 2 pi minus H1 bar times 2 pi. So if H1 minus H1 bar is an integer, it's well defined. Similarly, so if all of them are well defined, it's integers, it's well defined. That's basically the reason that it ensures that every correlation function is well defined. Okay, so it's easy to understand. Because another way of saying it is spin is what you use to take one operator around another. You rotate around that operator. Right, so if that spin is in integer value, it will be well defined. Okay, yeah. Yeah, sorry. Was there some other question? Okay, excellent. So now, what is the difference between this insertion and this insertion? Okay, so because this thing is because this thing here is infinitesimal, because this f here is infinitesimal, I'm going to expand everything infinitesimally. So for each phi factor, I get two things. First, I get what I get from expanding this, which is a factor of h del f by del z times the insertion of phi at z. This is not exactly inserted at z, it's inserted at w. But w and z to leading order, you know, I don't want to take two infinitesimals together. So I've already taken this factor, I won't take the second. Then I also get the second term, which is what I get by expanding the w dependence here. So I expand in a Taylor series. So I get del z, okay, del z phi times f. Now everything's evaluated at z. Okay? So this statement is equivalent to the statement that under a conformal transformation, the change in the operator phi is this. Because I have the original insertion plus this. Okay? Notice it's very important that I take into account both this term as well as this term. The fact that the position has moved, as well as the fact that so from this point of view, even a scalar operator transforms under conformal transformation. Even an h equals 0 operator transforms just because the position at which you're evaluating it has moved. That's the second piece there. Okay? So this is delta phi. But this should be what I get when I act with the generator of the conformal transformation that acts with the function f of z on the field phi. Okay? So what was the change in the operator? You remember we worked this out in the previous class? if I have a symmetry and I want to see how the symmetry acts on a particular operator, all I need to do is to consider the residue of the charge, of the current that generates the charge, which makes that symmetry, the residue of that current with the operator itself. So what's the current? The current is f of z times t, t of z. So it must be that residue of f of z times t of z with phi, let's say 0. Okay? The residue of, I do the OP, I do the OP and I concentrate only on the pole, I take the residue, that must be equal to this. That's the statement that this is how it transforms under conformal transform. Is this clear? Okay? Okay, so with that, we can now pull out, we can now deduce what the OP between T of Z and phi of O must be. Okay, so let's see. There is
commutator, right?
what?
It should be commutator.
The commutate, remember in level of these kind of operators, what we've had insertion of some operator here, and then we take this, the charge generated by f of z t of z on this contour, minus, as you said,
Right. Yeah.
the charge generated, since,
That is,
yes,
yeah.
but let me just write it since, if you're confused, maybe somebody else's as well, minus this, and then we can deform the contours in the usual way to get just that residue. So finally the statement is just a statement about the residue of this current with the operator. Okay?
Could this include the second term below the contour closes and the entire contour is coming from the term on the left?
Well, this is true.
The statement that the object on the left is equal to the right.
This is true if there's nothing here. But I could put lots of insertions in it. This would still be true. This is an operator statement. This is a statement telling you how an operator transforms under conformal transformations, no matter what other insertions there are.
I mean, but when you're doing the OPE, the statement is that you have sort of these two operators are really close and there's nothing else next to them, right?
Nothing else next to them, and that's all we will need for here. But it doesn't preclude there being other operators inside. We'll only do the OP between here and here. Right? So these guys will be very close, infinitesimal.
Just an isolated insertion.
Isolated, but there could be things here, there could be things here.
I mean, not in any small neighborhood.
Yeah, right. These things are infinitesimally close because when I take the commutator, I'm taking the limit that they're going to 0. Okay? Excellent. So, now how must this work? Well, this term comes without a derivative. That tells me that there must be a term from T of Z, phi of 0, which goes like, which goes like del Z phi by, let me call it W, Z minus W, I'll call it W. But this came with a derivative. Derivative meant we had to Taylor expand, so it came with the second order pole. So there must also be a term which goes like H phi of W by Z minus W square. And there's a plus between them.
These are all the singular terms of interest in the
Exactly.
Okay.
Exactly. First, let's check that if this is correct, then this residue is right. This is obvious, right? Because I take this f of z and I Taylor expand it around W. So I get f of W plus z minus W times f prime of W. Okay? And this works beautifully. Clear to everyone? Moreover, these can be there cannot be further singular terms. Because had there been a z minus W to the power n, then there would have been a term here with f n minus 1 of W of z. Yes, the n minus 1th derivative. You have kept differentiating till you got a pole. Okay? So this must be the OPE between the stress tensor and the primary operator. So if you've got a primary operator, it's primary according to our definition. And you know, people often say what I first said, phi is equal to del w by del z to the power h, that's 5z. But you have to remember what it means is what I said second time. Okay, that's what it means. Whenever you get confused, and sometimes it gets confusing, whenever you get confused about what it means, this is what it means. It's an equality between two functions of z's, computed in two different ways. Okay, that you have to keep in mind. Is this okay? Fine. So, right. So excellent. So what we've got is that if you have a primary operator, then the OPE between the stress tensor and the primary operator takes this form. Now the next calculation we're going to do is try to understand what we can say about what happens when Lm acts on a state dual to a primary operator. Okay? What does that mean in path integral language? What's a state dual to a primary operator? Well, I've got a primary operator which I insert at 0. This is phi. Then I do the path integral, it creates the state. Then I act Lm on it by integrating z to the power m plus 1 by 2 pi I t of z. What?
L1 analytic in particular.
Right. So let's see. That's yes, exactly. Let's see. So now what we do is to shrink this guy and use the OP. So we want z to the power m plus 1, and then we get h times phi of 0 divided by z squared plus del w phi by z dz. Okay? Now these are the singular terms. There could well be non-singular terms. Okay? So great. So let's see. So so everything else is non-singular. So let's see. What can we say here? If we have m, firstly, if m is less than equal to minus 1, all bets are off. Anything could happen. Because then this could be a singularity here, which meets something in the regular part, and we just can't say anything. Okay? So this is all bets off. Okay?
So this is because we sort of started off the computation this way, where we only can do the singular part. Is there just in general a way where you can figure out sort of the non-singular part and then you have to go to smaller, more negative ends?
Right. Now you see, the transformation of phi under conformal transformations, which is all that we know about, only controls the singularities of this OP. Okay? So the non-singular pieces are theory dependent. Okay? So we can't do better than this. We would need to know more about the theory. Okay? Because this is all we know about, because this tells us that if this is true, it will transform the right way. And that's all we know.
So this will hold for any conformal theory?
Any conformal field theory and any primary operator.
This is just kinematics.
Exactly. This is kinematics. Yes. Right. Equal to minus 1, sorry. I should have said less than. Less than. Thank you. Less than minus 1, all bets off. Now what about minus 1? M is equal to minus 1, let's try. del w phi,
The derivative of
you take a derivative
with
and then evaluate it at the position 0.
that
What does it mean inside a path integral?
as a limiting case, if phi at w and then phi at 0 by w and then take the
It-
I mean, from the definition of derivative,
From the definition of the derivative,
where the
where is it taken? Of course, you have some choice. But let's say phi at epsilon minus phi at minus epsilon divided by 2 epsilon. The limit epsilon goes to 0. Was that the question? Maybe I'm not understanding.
this is the question. I am just asking that is the 0 is a special point?
It's not a special point.
Okay.
You see, 0 is not special. It may be special when you think of it from a particular radial slicing of the path integral. But from the point of view of the path integral, it's any old point. In fact, there's translational invariance. It's clear that the 0 is not a special point. Okay, you know, the fact that so early in the course I introduced the state operator map has made all of you think of 0 as a forbidden point. There's a puncture there. From the point of view of the path integral, it's any other point. All points are the same. Okay? Okay. Okay, what about m equals minus 1? When m is equal to minus 1, this is not there. And so we get L minus 1 on phi of w. L minus, so I should write, what we've actually computed is the action of the state, on the state. So we get L minus 1 acting on the state phi of w. But by this notation, what I mean is the state dual to the operator phi of w. Okay, is equal to the state del w phi. Can you see that this is what you get? Because we'll take the residue, and then that will be the operator inserted at the origin. So you get a state dual to that operator. Now this was an entirely obvious thing, right? Yes. This is the argument we used to tell you that no operator other than the identity could be annihilated by L minus 1 because it's translated. When you translate, you pick up a derivative. It's totally obvious statement. Okay?
Could you make the statement again? I didn't have that. No operator.
Remember what L minus 1 was. L minus 1 was the operator that generates translations. Somewhere at the beginning of this class, we made the claim that no operator other than the identity could be left invariant under L minus 1. Because that was the statement that every operator changes under translation. Now you just ask, how does it change under translation? Well, it picks up a piece proportional to the derivative of the operator. Okay, so the change of the operator under translation should have been proportional to the derivative, and this is what we're seeing.
Yeah.
In fact, this part is not even necessarily true for primary operators. Just general statement about all operators. Any operator, the action with L minus 1 is a derivative of that operator. We saw it for T, which was not primary. We're seeing it for these guys. Okay, all good. Okay. Finally, what about m equals 0? Okay?
Just scaling.
Yes, just scaling. We get L0 on phi of w is equal to h times phi of w. Phi of 0. Phi of w. You see that from there? This is the statement that phi under a scaling transforms with weight h. Now, of course, we knew that. You see, how does a derivative transform under a scaling? Transforms with mass dimension 1. An operator with weight h is like h derivatives. So transforms with weight with dimension h. Right? It's just h times the scaling transformation of a derivative. This also we knew. The interesting thing about primary operators is that Lm phi is equal to 0 for m greater than or equal to 1. Okay? So remember the identity, the state proportional to identity was killed by all LMs from -1, -1, 0, 1, 2 up to infinity. The state dual to a primary operator is not killed by L minus 1, it's translated by L minus 1, is not killed by L0, it's scaled by L0. But then it is scaled by L1 to infinity. Good. Let's remember what the analog was for the identity operator. We had Lm on identity was equal to 0 for m greater than or equal to -1. Here we have Lm on for an arbitrary primary operator. If you look at the action of LMs on a state dual to an arbitrary primary operator, it's 0 for m greater than or equal to 1. Identity was special because L0 killed it. That's because the state proportional to the identity operator has h equals 0. Identity was special because L minus 1 killed it. That's because the derivative of the identity operator is 0. Okay? So primary operators are special. They're special because they're killed by an infinite number of LMs. Not as special as the identity operator, but nonetheless quite special. Okay? And they're labeled by one number, or two numbers, h, and I keep focusing on the holomorphic part, but there's also an h bar, which comes from the anti-holomorphic part of the current. Yes?
I just didn't catch the argument. What for which the more singular term in T phi OP?
Okay.
We figured it out from del phi. Now I can just keep on expanding that. I can have del square f term there.
Okay, but if you did, then the transformation would pick up a del squared f. But it doesn't. This is how it transforms under a conformal term. Remember, we had a definition of the primary operator by how it transformed under a finite conformal transformation. Then we specialized the definition to an infinitesimal conformal transformation. And we found that the transformation law was this. There was an f term and a del f term, but there was no del squared f term.
I'm saying that I can keep on expanding the infinitesimal transformation. I can expand it up to second order.
In infinitesimal parameter?
Yeah.
But that's not what we're doing here. On both sides, we're working to first order in infinitesimals.
Yeah, yes. I'm saying we know the information only up to this order. There might be higher orders which we just have not.
No. Let's first try to understand this. Let's work to first order in infinitesimals. Even to first order in infinitesimals, you could have had something with m derivatives of f. Because something's infinitesimal because f is small.
Yeah.
Its derivatives are not small. F is small in amplitude.
Yeah.
Okay? So had there been a term m derivatives of f, we would have seen it.
And just one question on terminal logical. So far, we have been considering the phi which is dependent on the holomorphic part. This is what is usually called a chiral primary, right?
What?
A chiral primary with the phi's, with just transforming under the transformation of z and not z bar.
Yeah, but you know, actually the way I use chiral primary is often in higher dimension. I'm not even sure if this is. There's certainly sometimes they're called chiral operators, so I suppose chiral primary. Yes, yes. But I want to emphasize that everything I'm saying here, I'm focusing on the holomorphic part just for convenience. The operator could have weight h under h holomorphic and h bar anti-holomorphic. Okay, and then this would still be true governed by h, but there would be an analog relation t bar on phi, the same operator.
Yeah.
Okay, would be h bar phi w. You know, when I say w, it's w bar. I'm not writing that. Z bar minus w bar squared. Okay, I don't by focusing on the holomorphic part, I don't want to give you the impression that we're only dealing with holomorphic operators. It's just that the same algebra works on the anti-holomorphic side, so I'm not repeating it.
and then L bar 0 will be
Exactly.
giving the weight
H bar. Okay? Just the algebra is repeated. The operator could well have both holomorphic as well as anti-holomorphic dimensions. You'll see many examples of such operators.
And all L and L bar operators commute as usual.
Of
right?
course, L and L bar commute with each other. Right? L and L bar commute with each other. What's the proof? Well, suppose I take a T bar OP. It has to be both holomorphic as well as anti-holomorphic. Firstly, it has to depend only on the difference between coordinates. Now, as a function of the difference between the coordinates, it has to be holomorphic, because it has to be holomorphic plus T is holomorphic. But it has to be anti-holomorphic, because T bar is anti-holomorphic. Therefore,
Stupid question. H bar is the H of T bar. It's not a complex conjugate of H, right?
it's not the complex conjugate of
It's the H.
H bar of T bar. And in general, operators could have different H and H bar dimensions. Of course they must, because H and H minus H bar is a spin. And we want to have the freedom to deal with operators with non-zero spin. Right? Can somebody check for me that H minus H bar is spin? Well, H is the eigenvalue under Z del by del Z. H bar is the eigenvalue under
Z bar.
so H minus H bar is the eigenvalue under del H. H del by del Z minus del bar Z bar del by del Z bar. Can you see that this is rotations in the plane? Because rotations face Z one way and Z bar the other. So this is the spin. So H minus H bar is the spin, eigenvalue under rotations. Surely there are operators which non-zero spin. For instance, T of Z is such an operator because it has H equals 2 and H bar equals 0. Okay? Good. Yes? What? Yes. Only for primary operators. Well, actually more honestly, it is always possible to form a basis in the space of operators such that your operators have all operators, primary or not, have definite eigenvalues under H0. How do we know this? Let's use the state operator map. Under the state operator map, L0 maps to L0 plus L0 bar maps to the Hamiltonian, and L0 minus L0 bar maps to translations on the circle. Okay? So, on the cylinder, L0 plus L0 bar is definite energy. L0 minus L0 bar is definite momentum. You may want to call it angular momentum, that's up to you. Motion in the circle direction. Okay? Now, these are symmetries of our theory. So we know that for states in the Hilbert space on the cylinder, it's always possible to find a basis of states that simultaneously diagonalize Hamiltonian and momentum. Because translations, time translations and space-time translations are both symmetries of our theory. So it's always possible to find, and these are we have strong theorems in quantum mechanics, right? So this is a basis of all states can be written in a basis of states in which these are diagonal. Therefore, the same is true of operators by the state operator map. So it's always possible to find the basis for which, in that basis, all operators have definite H and H bar. But you don't have to use that basis. You can, of course, take a linear combination, one operator with H this and another operator with H that, and that doesn't have definite H. Just like in quantum mechanics, while it's always possible to find a basis of states with definite energies, you don't have to use that basis. It's the same statement. Okay, good? Okay, great. So where were we? Fine. So I've told you about primary operators in general. Now, the last general thing I want to say, maybe a little more of representation theory. Come to that. We come to that. The last general thing I want to say before starting to look at special examples, and then we come back to some more general analysis a little later, just to prevent it from getting too abstract too fast. Okay? Yes.
This is in terms of a translation operator. So it's L of minus 1. L of minus 1 and L bar of minus 1.
Yes.
That expression has very good conformal transformation property. The action is right.
Yes.
You want to clearly nice
Yes.
under conformal transformation.
Yes.
So you construct that in terms of this operator which are nice primary operators.
Yes.
And action of those operators is on the primary operator.
Yeah, like derivatives, you say. Yeah. Yeah. Yes. Okay.
I'm leaving it out because
Yes.
I want to just,
Yes. Yes.
So L minus 1 in particular are usual kind of
Exactly.
Lagrangian.
Exactly.
You put other operators and can you not create that kind of Lagrangian quite easily?
Ah. So your question is, if you start with L minus 2, for instance,
You have one derivative yet, but
if you start with L minus 2 times L minus 2 of a primary operator, will it be D2Z? Will it be conformally invariant? That's the question.
can you please easily build such Lagrangian?
Well, yeah. I don't think it will be possible. To start with, for it to be conformally invariant, it has to be invariant under weight. Okay. So whatever you want, you see dz bar, okay, times whatever you have should at least be invariant under scaling. Okay. So if you start with derivative on something of dimension 0, naively of dimension 0, okay, this will work just from weights. But if you start with 2 derivatives, you'd have to start with something of dimension -1. Okay. Moreover,
You are experimenting that L minus 2 and L0 has some operator algebra. L0 and L minus 2 has some commutation relation.
yes, exactly. L0 and L minus. So we want this to be invariant under all conformal transformations, in particular under L0.
Yes.
Okay. But so if you start with L minus 2,
Oh, that's the statement that, sorry, that will be probably the statement that with these operators, if you take commutations of other operators, not SL2 part, but let's say minus 2, minus 3, they will not prove.
exactly. It'll be very difficult. But even without looking at something as sophisticated as what you said, you already see just from weights that you would have to start with something weight -1. That's already problematic. It's not going to be easy, at all.
Yes.
Yeah. Okay, let's keep going. Yeah, but by the way, just to complete this, if you start with a Lagrangian that looks like this, where O is any weight 1, 1 operator, 1, 1 conformal operator, some object that transforms like 1, 1 under conformal transform, that's going to be conformally invariant, because the change in measure of Z exactly cancels the scaling, the transformation of a 1, 1 operator. So naively what you want is a 1, 1 operator as the Lagrangian density to make something conformally invariant. Now how you make that is up to you.
So 1, 1 means it is the primary operator with H is equal to 1, H bar is equal to 1.
What H is equal to 1 and H bar is equal to, exactly. Okay? And in the case of this free scalar, as you know, you might think you were starting with a dimension 0 operator, but that's false. That's not really an operator because of the infrared divergence.
Yes. So only derivatives are the operators.
And the derivative is a primary operator of weight 1, 1. Yeah. So that's really what you need. You see, anything other than, there's only other issue. The only other issue is total derivatives. You might hope you can get away because of total derivatives. But naively, the only way you can work is with a 1, 1 operator. If you want this to be invariant, not up to total derivatives, then the only way it can work is if you have a 1, 1 primary operator. Okay. Yeah. So maybe the last thing for today before we close is the following. Okay. Suppose suppose I take the sphere. Okay, so suppose the space on which I'm inserting everything is a sphere, or the plane, or the plane with infinity treated the way we treated it in the beginning of this class. That is, if you ever get confused about whether something's regular at infinity or not, do the z goes to 1 by z conformal transformation and ask for regularity. Okay. If I do this and I look at correlation functions on the plane, okay, all correlation functions have to be invariant. All correlation functions have to be invariant under SL2R transformations. That is the transformations generated by L minus 1, L0 and L1. Why is that? The reason for that is very simple. I've got all these correlation functions. And then I start, so this is the correlator that I'm interested in. Okay? And then what I do is insert the generator of conformal transformations, the one that I'm interested in, L0, L minus 1 and L1, okay, around a little region around 0. Okay? Now, I also insert something like this around a little region around infinity. So a big circle around infinity, but a little circle around
The point at infinity.
the point at infinity.
That was this point that identity operator is.
It's killed by it, yes. Okay. Now, this is going to be 0 because I can close this contour around the circle. So remember that this thing annihilates the vacuum in the 1 by z quadrant. That's the same argument we gave in quantum mechanics, but now made more precise. This is going to be 0 because identity operator is annihilated by, and remember L0, L minus 1 and L1, sorry, L minus 1, L0 and L1 under inversions, under z goes to minus 1, map to L1, L0 and L minus 1. Okay? So this thing here, obviously each of these three operators, exactly, KMU difference. Yes, clearly this guy gives 0 because I can just shrink this contour. But because this guy also gives 0, because I move to the other coordinate, and SL2R operator remains in SL2R, and then it annihilates that vacuum.
Dagger is in fact some.
Exactly. Is this clear? So I'm just making a precise version of the argument we've already made earlier in this class. But it's nice to have these things precise. Okay? So this contour integral, the contour integral, what I really want is this minus this is equal to 0. Okay? But that is the same thing as each of these is equal to 0. Maybe another way of saying it is I start with the statement that this is 0, and then I shrink the contour down to this point and shrink it through at the origin. But what's left behind is a contour enclosing each of these operators. Is this argument clear? Was that too fast?
Could you just
I'll start again. I'll repeat one. I've got some operator insertions. Now I start with the equation 0 is equal to this, where that contour represents the integral of a current for an SL2R generator. How do I know it's 0? I know it's 0 because I go to the 1 by z coordinate and I close it, shrink it to nothing. I act on that vacuum and I check that SL2R annihilates that vacuum. We check that somewhere in the middle of this class. Okay, so this is equal to 0. Now I use complex analysis. I use Cauchy's theorem to tell me that just by complex analysis, this is equal to plus this when this is enclosing 0, But then this is also 0, so I can ignore that.
You don't have to restrict to this particular the one that you wanted. In the sense that if acts on other operators, on general operators for this negative elements are not known, you have no base for them.
Yes.
But for identity, there will be derivative of stress tensor.
Yes.
So that you know some information, so that you can again use.
We can use and get something more complicated.
More complicated.
Yes. And we will
Still there.
yes, and we will do that. Okay. Yes, yes, yes. But right now we want to use the simplest thing. Okay? So what we have here is the statement, but this was equal to 0, but this was equal to this. So this is 0. Okay? But this is just a sum of residues. The sum of residues for the current for the SL2R generator with each of these points. It's just how each of these operators transforms under the symmetry operation. Just how each of these operators transforms under the symmetry operation generated by the SL2R. So what is the statement we've derived? We've derived that if you've got some correlation function, so O1, O2 to On, okay, then sum over n, okay, delta O1 plus O1 delta O2 plus O1, O2 delta O3 and so on is equal to 0, where delta O is this residue. It's the change, it's the transformation of the operator under the charge generated by the SL2R transformation. Okay? Now, let us recall how a primary operator transformed under SL2R. We had that written down, but I'll write it again. L minus 1 of phi was equal to del phi. L0 of phi was equal to 0, and L1 of phi, sorry, H phi, and L1 of phi was equal to 0. Okay? We also had that a primary operator had L2 and L3 and L4 and so on, annihilating the operator. But all we're going to use for what I'm going to be doing in the next 10 minutes is these three relations. Now, there are many operators that obey these relations without also being primary. You see, this is true of primary operators, but primary operators will be much more, because L2 on phi is 0, and L3 on phi is 0, and L4 on phi is equal to 0. There's an infinite number of conditions. Any operators that obey just these three relations and not those other infinite numbers of relations are called quasi-primary operators. Okay? So everything I'm going to say over the next 10 minutes is certainly true of primary operators, but it's true for a larger class of operators, namely all quasi-primary operators. Okay? All that is required is that the quasi-primary operators are annihilated by L minus 1, sorry, L1, but not by L2 up to infinity. That's not needed for what I'm saying now. What I want to do is to deduce the forms of 2-point functions and 3-point functions. The functional dependence of 2-point functions and 3-point functions of quasi-primary operators. Using this information, that L minus 1, that using this equation, where this delta O is given by those statements there. Okay? Clear? So let's start with 2-point functions. Suppose I've got an operator O. Again, I'm going to talk only about the holomorphic part. The anti-holomorphic part is going along for the right. Okay. So I've got an operator O with weight h at Z1, and operator O prime O tilde with H tilde at Z2. I want to look at the 2-point function of this game. First thing I use is the statement that L1 annihilates the 2-point. What does the statement mean? I'm supposed to act with L1, L minus 1. L minus 1 on this guy unchanged, plus that guy and L minus 1 on that guy, and I should get 0. Okay, so this means that del Z of OH of Z1, OH of Z2, plus OH of Z1, del Z of OH of Z2, this has to be equal to 0. This is what it means. But what does del Z mean? You see, what is del? I said this before, but it's worth hearing again. What does it mean to insert within a path integral the derivative of an operator? It means insert the operator at Z, calculate your correlate, minus insert the operator at Z plus delta Z, calculate the correlate, and divide by Z plus delta Z. That's what it means, right? Because within the path integral, derivative is phi of Z plus epsilon minus phi of Z divided by epsilon. And then you compute the path integral for each term separately. Which means that this, in the path integral, is just taken outside. Is this clear?
So this statement is true for any operators, not necessarily for the primary, because we're claiming that all point functions are invariant under
Exactly.
SL2 transformations.
What? All point functions?
This
This first statement is going to be true of all operators because all operators transform like this. Not just quasi-prime, because this is just a statement of translations. The remaining two statements will only be true of quasi-prime. Because not all operators transform in that sense. Okay? But this is a general universal statement. Okay? You're going to see we get a general universal answer. So now this thing is some function of Z1 and Z2. So it's sub G of Z1 comma Z2. But we found that del Z1 plus del Z2 of this function is equal to 0. What does it mean? It means that G is equal to G of Z1 minus Z2. Doesn't depend on the center of mass coordinate. This is translational invariance. Okay? I could have written down from the beginning and nobody would have objected. But you know, the same logic that will give us everything else also gives us translation invariance. So let's, fine. Okay. Great. Now, which statement? Does pulling the Z out? Del Z out?
So all this, the result you are going to derive, they will be up to contact terms.
The result I am going to derive will be true up to contact terms. I don't even see why. Well, yeah, okay.
You can put a delta function of Z1 minus Z2, but
That is a function of Z1 minus Z2.
for Z1 minus Z2.
Uh-huh.
But you are going to use other sizes, right?
Yeah. So you're saying that this statement.
Within this three operator, three equations,
Mhm.
you are going to derive some particular form of equivalent function.
Yes. And you're asking where contact terms can sit in that. You know, yeah. It's probably it's probably true that things get more complex. It's true that in my way of thinking of, for instance, when I wanted to transform operator 1 separately from operator 2, you know, in this contour thing, I'm assuming they're not sitting at the same point. Okay, so let us assume that the operators are distinct points. Yeah, you're probably right that there could be contact terms, which this argument may be too nice. This contour argument sort of sees that.
Yes, yes.
Because it assumes that the operators are at distinct points. Because otherwise you're getting a composite operator when you're putting them together.
Yes.
Yeah, so I think you're right. Let's make sure that the operators are at distinct points, no matter how close, but at distinct points. So anything that's purely delta will not be, it may not be constrained by these arguments. Okay. And it's certainly true that in conformal field theories you often have interesting contact terms that these arguments or the higher dimensional analogs don't effectively constrain. Yes, and these will be connected.
At this stage, how they're different.
Yeah, exactly. So let's separate them. Let's separate them. I think you're right. Okay, good. So we've concluded that these correlation functions depend only on Z1 minus Z2. Now let's do the same thing with L0. Okay, what are we going to get? Can you see we're going to get H plus H tilde on G, which is now a function of Z1 minus Z2. Z2, except that we have to be careful. Okay, except that we have to be careful because this thing, this thing, now how did something transform under one of these conformal transformations? Okay, there was this, but there was also the action on the coordinate. Okay, and that we have to take into account. Okay, so let's see. So there was this, but there was also the action on the coordinate. Now why did we, this statement was completely true, you know, of the states at the origin. Okay, this statement was completely true of the states at the origin, but now, where am I getting that second term from? Just a minute, from my derivation, just 1 minute. Let us look at it a little more carefully. Okay, so let us look at it a little more carefully. I was a little careless because I was, earlier parts of the manipulations, the things were inserted at the origin, and the remaining terms that I'm going to get were absent when it's inserted at the origin.
Fixed point for the
Scaling, and also for the conformal transformations because of the Z square. So I have to do it more carefully. And we're running out of time. But let's quickly at least sketch the argument. Okay. So let us now look at these quasi-primary operators. So let's see. What we had was, remember that for a primary operator, T of Z times phi of W went like H by Z minus W, the whole thing squared, plus del phi by Z minus W, and no other singular terms. For a quasi-primary operator, all we care about is the transformations under L0, L minus 1 and L1. You see, that is this statement saying that there could be regular terms and there could be more singular terms. That will tell you how it transforms under the higher LMs. We don't care about that. So all we're going to do is so the quasi-primary operator is something such that the pole is given by this in the OPE, and the double pole is given by this. There could be higher poles, and there could be regular terms. Okay. Now we will carefully see what the transformation of a quasi-primary operator at a non-zero point is. So let's see. So under the L0, L minus 1 actually we didn't write. You'll see why. BCA. Yeah, you Baker Campbell House stuff. Yeah, you could, but let's do it by contours. Yes. Okay. So now suppose we've got something inserted at the point Z1. Let's call it W1. Okay. Now you remember the thing that we had to have, the the delta O, was the residue of the operator. Okay, so what do we have? We have, so let's do it for the scaling, for instance. So the current was Z Tz for the scaling operator. Okay, and we're supposed to take the residue of Z Tz with the phi at we get Z Tz plus we get so let's see. So we get this with phi at W. Let's say it's W. I want to find the residue of the pole. So this is Z times H by Z minus W, the whole thing squared, plus del phi by Z minus W. It should be, sorry. What? Yeah, and now I want to expand I want to expand Z around W. So I will get a term which is W times del phi. That's the term that was absent at 0 because W was 0 at 0. Okay, so that's why I was fooling myself before. Okay, plus the term we kept, which is just, then I expand this in Taylor expansion, H phi. So the full residue is this. Okay, so now you see what the right equation is. The right equation is that every operator transforms by W del W plus H. Okay, so the action on this, on Z1 times G of Z1 minus Z2 is Z1 del Z1 plus H plus Z2 del Z2 plus H tilde on G of Z1 minus Z2 is equal to 0. Now what is this equation? This equation tells you that in the variables Z1 and Z2, this function has homogeneity minus of H plus H tilde. Now what function do you know which is a function of Z1 minus Z2 which has homogeneity H minus H tilde? So this has determined this thing to be 1 over Z1 minus Z2 to the power H plus H tilde. Okay? Is this clear? Now, the last thing we'll do, and then we'll stop, I'll leave 3-point functions as an exercise for you guys and check it next time in class. The last thing we will do is to act with L1. Okay? Now, L1 phi was equal to 0 at the origin. We won't make the same mistake twice. We'll just use the OPE once again. All that we have to do for L1 is to put a Z square here. Okay? So all that we have to do for L1 is to put a Z square here. Well, let's use the okay, let's quickly do this. Okay, so this was del phi Z minus W. Okay? So what we want to do now is exactly. So we'll Taylor expand this. There's a W squared T of Z plus W Z minus W T of Z plus 2W Z minus, thank you, plus second derivative. It will not matter, yeah. Okay. Exactly. So we need to take these two terms. Yeah. So now this guy with this guy gives us W squared del phi And this guy with this guy gives us plus 2HW phi. Okay? So now what we have is a differential equation. We have Z1 squared del by del Z1 plus 2H Z1 plus Z2 squared del by del Z2 plus 2H Z2 acting on 1 by Z1 minus Z2 to the power H plus H tilde is equal to 0. Well, let's see. H tilde. This is H tilde. Thank you. Thank you. Okay, so let's see what we get. When we differentiate with the first guy, we'll get Z1 squared by Z1 minus Z2 to the power H plus H tilde. Yes, H tilde. Into H plus H tilde with a minus sign. Yes, and then we get the same thing with Z2, except that this came with an, this came, so minus Z2 squared H plus H tilde by Z1 minus Z2, the whole thing to the power H plus H tilde minus 1. And now we have to be a bit careful because we took a Z2 derivative, which is minus, so this is probably a plus.
One of them will get a minus sign, and then Z1 plus Z2 terms, one of them will cancel.
Exactly. Exactly. Okay, and now let's look at the other two terms. The other two terms are just multiplying. So you get plus 2 into HZ1 plus H tilde Z2 over Z1 minus Z2 H plus H tilde is equal to 0. And this looks like a strange object. I mean, is this true? You can try simplifying for all you're worth. When H and H tilde are non-zero, it's not are different. It is not true. Okay? So let's try simplifying. So let's add a plus 1 here. And we add a Z1 minus Z2. Now we've got the same denominator all through. So the numerator has to vanish. So we get the quadratic equation minus Z1 squared H plus H plus H tilde into Z2 squared minus Z1 squared, okay, plus 2 HZ1 plus H tilde Z2 Z1 minus Z2 is equal to 0. And unfortunately, for arbitrary H and H tilde, this equation is just not true. So what's wrong? However, notice that as Indranil pointed out, let's look at the special case H equals H tilde. If H is equal to H tilde, then this becomes 2H. This also picks up a factor of 2H, and this is Z1 plus Z2 into Z1 minus Z2. So that's Z1 squared minus Z2 squared. This was Z2 squared minus Z1 squared, so they sum up to 0. Okay? So for arbitrary H and H tilde, this, remember, I had to work for every Z1 and Z2. It's just not true. But when H is equal to H tilde, it is true. And only when H is equal to H tilde is it true.
Hamilton does not decide
Okay. So what this tells us is that there is no non-zero two-point function between quasi-primary operators of different dimensions. Okay? If you take quasi-primary operators, they have non-zero two-point functions only if their dimensions are the same. This we will see in Hilbert space language is connected to the fact that states have non-zero inner product only if their energies are equal. This 2-point function will be connected with an inner product of the corresponding states. One inserted at the origin and the other inserted at the so
The operators are these particle antiparticle.
particle
This is
antiparticle.
why you need to
Exactly. Okay. So we deduced something very nice. We deduced the form of 2-point functions. So the O H with O tilde of H, only when H is the same as 1 over Z1 minus Z2 to the power 2H. Okay. Now I'm going to leave the next statement I make as an exercise for you guys, and please do it by the next class whenever that is. Tomorrow's a holiday, I hear. Okay. I need to schedule some extra classes. We'll try that. Okay. So the exercise. Show that if you have 3 quasi-primary operators, show that if you have 3 quasi-primary operators of dimensions h1, h2, and h3, then that 3-point function, the holomorphic part of the 3-point function, okay, must transform like z1 minus z2 to the power h1 plus h2 minus h3. 1 by z2 minus z3 z is a half needed instrument. I'll check. The dimensions are working out to no, it's working, I think, right? Because let's check. Let me write it and then we'll check. Yeah, z2 minus z3 to the power h2 plus h3 minus h1, and z3 minus z1 to the power h3 plus h2 h1 minus h2. Now let's add up all the dimensions. All h because appeared. Yeah. Exactly. Okay. Exercise. Show that 3-point functions are forced to be of this form with some number, just by using the same logic. All right, we'll talk about 4-point functions in the next class, and then we turn to specific. Okay, that's it. I'm sorry for going over time. Yeah.
Number is just
Which?
you fix it up to a number.
I fixed up the number, then this could have been arbitrary.
Just some dimension.
Convention, you can rescale your operator. What is not a convention is the number that appears in 3-point functions once you've chosen 2-point functions to be. What? For stress tensor. Or even just you choose these 2-point functions here to appear with 1. What do you mean for stress tensor?
If you have stress tensor, then the operator product expands are 4 to 2-point function of stress tensor.
The 2-point function. You're saying that the number behind 2-point functions of stress tensors is well defined. That's what you're saying? Yes, that is true because the stress tensor has a definite meaning. It actually generates translations, it generates coordinates. Yeah, this is true. For stress tensors, there's a preferred normalization. For general operators, there's no preferred normalization. You can always rescale them to have 1 here, but then the 3-point functions become meaningful. Sorry, what were you saying?
So once we fix 2-point and 3-point functions, that will in turn determine all higher point functions.
That determines all higher point functions by conformal bootstrap. It's true. It's true. By the OPE basically. It determines the OPE and then determines everything in principle. If you know 2 and 3-point functions of all operators. So the CIJKs, the 3-point function coefficients are very important.
No, once we just come back to your earlier point, once we rescale the 2-point function to
that's what you were saying.
Coefficient,
Then-
I mean, this is another question.
Then the coefficients that appear behind all higher point functions are completely unambiguous.
I see. Including 3-point functions.
Including 3-point functions. Because the 2-point function gives a particular definition of the operator. It fixes the rescaling ambiguity, and now it's fixed.
You will probably tell us why modular transformation is sufficient for everything. I mean, in higher genus surfaces, let's say genus 2, you might have new constraints. When you going from sphere to torus, you ended up getting a new constraint, which is modular transform.
Yeah, why don't you get it at dimension 2? I think there's a theorem about, I don't even know why. I'll try to find out. Yeah, I don't even know why. It's probably, is it even true that if a theory, I think that yeah, there's a theorem. So if a theory obeys the OP as well as and is modular invariant, then defines well-defined correlation functions and all these.
So that is something extra.
Yes, it's something extra, and we don't even know what the analog of that extra thing is in higher dimension. In fact, the modular transformation, the transform for modular transformation goes for 0 point functions and 1 point.
0 point functions and 1 point functions.
So there's a partition function